So the complementary solution, which is a solution for the homogeneous second order differential equation, results in a characteristic equation which is just simply a quadratic formula that has a couple of roots. So if it happened to be that alpha is less than omega 0, what I'm effectively telling you is the characteristic equation here, it has a discriminant that is simply greater than 0. It's a real number. Because it's a real number, that means this one here is a real number, this one here is a real number, that means S1 and S2 are real numbers, and as it turns out to be, well, this is a positive number, and negative in here, but alpha is a positive number, that means the S2 is a negative, and also you'll see, well, this one here is less than the alpha, okay, even though that we're adding to it, well, alpha is larger, so it's going to be negative. So if we're actually plotting on the S or complex S domain, so let's assume that this is complex S domain, this is real, this is imaginary, what you'll end up with is the following. You'll end up with some sort of an S1 and S2 maybe in here. Something similar to that. Maybe this is here is S2, this one here is S2. So both are real and distinct. So let me just write it. S1 and S2 are real and distinct. And if this is the case, what we end up with is what we call the overdamped response. So the overdamped response tells us that the solution for this here is just simply X. Well, the complementary solution will be simply K1 e to the power S1 of t plus K2 e to the power of S2 of t. And of course, if we want the full solution, all you have to do is just tell me, well, it is simply the, well, let's keep this complementary. So the full solution X of t is simply the particular solution plus the complementary solution, which we just found out, which is just simply K1 e S1 of t plus K2 e S of t. All right. And of course, we can substitute what S1 and S2 are. And they're simply the following. So X of t is xp of t plus K1 e to the negative alpha t, for example, e to the negative alpha squared, omega 0 squared. There's a negative in here, t, plus K of 2 e to the negative alpha t, e to the negative alpha squared minus omega 0 squared in here. And this is also multiplied by t. I think this would be a positive in here. Well, we did S1, so let me just do this here. That will be the positive in here. All right, so this is the solution, and just to reconfirm, so the Neper frequency alpha is sometimes also called the damping coefficient, because if you take a look in both cases in here, this one and this here, if you wait for enough time, you will see that whatever you're doing, it just basically will be decaying with time, and that's why it's called the damping coefficient. So it's dampening this solution. The complementary solution is just dampening and going away. All right, so and to reiterate, what we have in here as well is we have a couple of constants in here. These are K1 and K2. So in order for us to find K1 and K2, what we need is a couple of initial conditions so that we end up with two equations so that we can solve it and figure out what K1 and K2 are. So for example, we can say, well, at t0, we can substitute x equals 0, and that will give me simply xp evaluated at 0 plus k1 plus k2. You can substitute the t is 0, that's a 1, t is 0 is 1, so that tells me k1, k2, and xp evaluated at 0. So this will be the first equation. Okay, the second equation will be when you take the derivative of the dx of t divided by d of t and evaluate that derivative at 0. What you'll end up with is the following. You'll end up with k1 e to the power, well, no e, it's actually s1 plus k2 s2. That's what you'll end up with. And you can take the derivative. This is here. You can take the well, we know the xp of t for dc is just the derivative of this will be 0. The derivative of this while t is 0 is just simply k1 times s1 e to the power s1 of t, but we'll evaluate it at 0, so that leaves me with k1 s1. That's what you see in here. So these are the two equations, and once you solve them, you'll end up with a solution, and that solution will happen, there's no oscillation in here. That's why we call it the overdamped.